technology. Where did Justice go? I was gonna use you. Good morning, everyone.
Morning.
Um, okay, I'm going to get started right away. Hopefully more people are going to start joining, but we have a lot to cover. So I am just going to start talking. You should see my screen. You should see the slides that I've prepared for this presentation. So thank you all so much for being here for the first session of the Advanced Art Book Club. I'm hoping we'll get some more people from outside the Bugzip DB group. I was hoping some people from Levi's Lab would join as well. Well, hopefully some of them will show up. Um, so the goal of this book club is to read the book Advanced R by Hadley Wickham, and we'll go chapter by chapter presenting. Today I will present chapters 1 and 2. We'll meet every Friday at 11 a.m. Eastern Time. The presentations can be as informal as you want. You can sign up to present at this link here, and if you need this link, just message me and I can send it to you. And I will give you the incentive that if you sign up early, if you sign up now, you can pick an easier chapter. You know, there are some chapters that are harder than others. So if you want to make this easier on yourself, now's the time to sign up. I think Jackie is the only other person who signed up. So thank you for doing that, Jackie, by the way. And again, the presentation, just to give you a sense of how I prepared for this, I spent about, I don't know, 30 minutes reading the 2 chapters and kind of getting an understanding of it. And then I spent about an hour to an hour and a half putting together my presentation. So really the preparation for it is not significant. And you know, again, make it easy on yourself. If you don't want to make your presentation in R like I did, you could just do a PowerPoint. You can do whatever you're comfortable with as long as you're presenting the materials. Um, and so with that, I'm just going to get into it. So we'll be talking about chapters 1 and 2. 1 is the introduction. We'll go through the introduction pretty quickly. It gives some reasons for why R is good. You know, we're probably familiar with a lot of these reasons. The one thing I will note is that, you know, it's designed specifically for stats, machine learning, visualization, data management. When compared to tools like Python, that is a key difference. And it's really easy to connect it with other languages such as C, Fortran, and C++. I don't know anything about those languages, but that is apparently a selling point. Um, the book does give some interesting reasons to not use R, which I think were kind of interesting to me. So one thing that Hadley talks about is that there's a lot of bad code kind of floating out there in the world. If you Google an issue you have with R, um, often this is because people who write code for R are very results focused rather than process focused. So they'll develop something that gives them the right answer, but maybe it's not the best way to do it. Maybe it's inefficient. Maybe it doesn't work in every situation. Um, Hadley also says that some functions are inconsistent and they can use tricks to like get the right answer again in certain situations, but this can cause a lot of inconsistency and they can fail in weird ways and it can be really hard to figure out why something went wrong. And R, compared to some other languages, is not very fast and it uses a lot of memory. So despite that, we will go forward with R. Um, Hadley recommended this book for intermediate R programmers and programmers with experience in other languages. I consider myself pretty much a novice R programmer, and I have a tiny bit of experience with like Visual Basic, but I was still able to follow, my chapters in the book. Okay, so I think we can press on even if you don't consider yourself one of these two things. And this book is focused on programming. So it is focused on understanding how R kind of thinks about data, how it thinks about functions and operations, and objects. And it's very focused on kind of how do we improve our code, how do we solve performance bottlenecks, and how do we write code that is. Oh, we got some more people joining. How do we write code that is good, that is understandable and is high performance. So just to note that this book is not about data science skills, and it's not about creating a complete R package. If you want those, there's two other books that have been developed by, I think the first one is by Hadley. One is, I'm not sure if R packages is, but there's two other books you can consider if you want to learn about data science or actually making a package. The book then recommends two meta techniques to really improve your skills as a programmer. The most important of those is reading source code, just like any language, just gaining exposure to that language is probably one of the most important things you can do to learn it. And he recommends looking at source code of functions you use often, and just seeing what it does and why, and trying to figure out what it's doing. And then he also recommends adopting kind of a scientific mindset, which should hopefully be pretty easy for us, which is where you think of code development like an experiment. We hypothesize, we say like, I think the code I'm writing, this is what I want to do, here's how I think I can get there. I try writing something, I see what that produces for me, and then I iterate based on that. I say, okay, that didn't work, but it got me one step further, so let me go back and try something else and then see what it does. And so really thinking of this, the goal is not to write perfect code all the time right away. The goal is to like learn from our mistakes and, iterate from there and get better. He also recommends some other books. I don't think you really need to go out and get these, but if you want to learn more about kind of his thought process in developing the advanced R textbook, you can probably check these out. I checked, they're all on Amazon. I don't think any of them are available for free. Finally, he says if you need help, there's two things you should do, which is make sure you have the latest version of R and the packages you're using. And then create a reproducible example. A reprex is the short term. And that should be a self-contained code snippet that reproduces the problem you're having, because then you can share that with others and they can see the problem you're having and help you troubleshoot. With that is the contents of the introduction. So I know I went through that really quickly, but that's because the next bit is going to be much more important. So chapter 2 is about names and values. And this is when we're going to get into the actual kind of meat of the text. So I will go a little slower on this and try and talk through it. And if you have anything to add, feel free, because some of this stuff I'm very much learning about for the first time, even though I've written a ton of code in R, a lot of this was new to me. So feel free to chime in, and if you have questions, put them in chat, and we'll talk about the exercises together when we reach them. So there's an introduction, but the most important thing is that we start getting into what a variable is and what does it mean to bind to it. So he asks the question, what does this do? So we've got some object S, and we assign, or X, not S, X, and we assign, this vector of 1, 2, 3 to it. So what is this actually doing in R? When I was first learning R, I would say, oh yeah, I created an object X that contains the values 1, 2, and 3. Well, this is creating an object that contains a vector of values. it then binds that object to a name X. And so the important point is that the object itself is not X. The object has been assigned the name X. So the object is the vector of 1, 2, 3, which has been bound the name X to it, which is what this diagram represents. So the actual object is shown in these squares, and then we bound a name X to it. And this is important. The way I was thinking about this is that like, an object is separate from its name, and we can give something multiple names. For instance, I think about my cat, and like I have like 1,000 different names that I call him, but he's still the same cat. And it works the same way in R. We could assign several different names to this vector of 1, 2, 3, but it's still the same vector. Yeah, so the object is the vector of values itself. And you can see this. The way R treats this is if we then assign, another variable called y, and we say, okay, bind, x to that, we've just added another name to that underlying object, but it does not create a copy of that object. So in R, we have not actually created two objects called x and y that both contain a vector of 1, 2, 3. In fact, we have just bound the names x and y to the same object. And we'll see, like how you can determine that in just a second. So you can use this library lobster and to convince ourselves that this is actually what R is doing. We can look at the object address, which is the unique identifier that R is assigning to the object. So, we have our kind of identifier, which is the name that we've bound to it, but then R actually has like a hidden secret name that it uses that's a lot longer and harder to look up, and it's going to change if you, do this again after closing R. So like this is something that's kind of behind the scenes. But if we look at the object address for both X and Y, it is the same because they're the same object. This was mind blowing to me because I really thought they were separate objects when I would do something like, putting, when I would assign, Y to X, but they are still the same object.
So they can be used interchangeably or
So not quite. We'll talk about what happens when you modify one of them in a second, and why that changes things. So they are the same object, and but if you perform an operation on one of them, change it in some way, then the situation is going to change slightly. So that was a good question, and we'll see that in the next subchapter. The other thing this chapter notes is that names in R, the names that we bind, are important. R has strict rules about valid names. They need to consist of letters, digits, a period, or an underscore, but it can't begin with an underscore or a digit. You also can't use reserved words like true, null, if, and function. But you can override these rules by surrounding the variable name you want with backticks. So here, this is invalid because we can't start with a underscore, but if we put it in backticks, we can still use it. And same for if, even though that is a, like a core function in R, we can still assign something to if. But when we refer to it, to that variable, we always have to use the backticks going forward to distinguish it from, like the function if. So that does have that limitation of if you do name a variable this, you will always have to use backticks going forward. So we get into some exercises. So we'll start with this one. Explain the relationship between A, B, C, and D in the following code. Any thoughts on what these are?
Aren't they all the same?
So I do think A, B, and C are the same. I wasn't sure if D was the same. And so why don't we look in R and take a look at the object addresses and see what's going on. So we just make a new. Yep, we can copy and paste this. And run all this, and then we can say obj address. Oh, I don't know why it. There we go. We can take a look at all of them and see what it actually did. So we can see that the first three are the same, right? Because they're all this fancy thing, but this last one is different. And that's because we defined a new vector here. It's not this, even though it has the same values, we defined it again, so it is a separate vector, so it has a separate object address. Even though it's identical. So I would say that A, B, and C are the same, but D is a different object.
Why is that important?
Why is that important?
Yeah, for us to know that.
I'm not sure quite yet why this will be important. I mean, I think there are some important consequences in terms of memory usage. That you know, all in this case, you're able to refer. You've assigned 3 different names to the same object essentially, and you've conserved memory by not creating 3 copies of that object that are all the same thing. That doesn't seem very important when our object is only a vector of 1 through 10, but especially in the type of microbiome work we do, where you can have, you know, data sets where you've got several gigabytes of data, being able to kind of copy things like this without actually creating a copy of it right away, I would say maybe becomes important in terms of memory conservation. And there will be an allusion to that later on in this chapter, but I'm guessing it will come up more in subsequent chapters why this is important in terms of memory. So the following code accesses the mean function in multiple ways. Do they all point to the same underlying function object? And again, you can take this and just put it through this object obj underscore addr. I won't belabor the point, but you can try it on your own. I think they're all the same. So they're all just different names for the same function, which is to get the mean of some set of values. And then by default, base R data import functions like read.csv will automatically convert non-syntactic names to syntactic ones. Why might this be problematic? What option allows you to suppress this behavior? So I was thinking about this in terms of my own work, and I can answer. You know, if you've got some variable names that I don't know, like you need them to exist and you need to know what those variable names are, and it converts it to something else, that can, you know, be annoying to deal with, because then the variable that you expected to be in there is no longer in there, and you have to find out what it's been renamed to. And then you can, there are options to suppress this. I think if you look at match.names, there's a way to look at it. Let me see what the book said about it. Make.names, that's what it is. So you can look at the help documentation for how it decides to, you know, force syntactically valid names. It looks like you can kind of turn it off. So if you are interested in how to rename things, you can look at make.names. Okay, I'm just gonna keep going because we got a lot more to cover. What rules does make.names use to convert non-syntactic names into syntactic ones? You can check make.names, the documentation, and find out about the rules it's using. I slightly simplified the rules that govern syntactic names. Why is .123E1 not a syntactic name? Read make.names for the full details. I looked this up. It's because if you start your variable with a dot with a period, the next character has to be, whoops, the next character has to be a letter. It can't be a number. So it could be .A23E1, but it can't be .123E1. It's just a rule. I don't know why, but that seems to be the case. So just if you, for some reason, want your variable to start with a dot, make sure the next letter is or the next character is a letter. So now this is kind of getting into the question that Mary came up with, like, what happens if we modify y when we've assigned x. So this is, that same example we were just looking at. So we've got a vector x that contains 1, 2, 3. We then we bind the name y to it as well. But now we've changed it. We change the third value in this vector and we assign it the value of 4. So now we look at x, it's still 1, 2, 3. Modifying y does not modify x. So what happened to the shared, binding? They were the same object. Well, if we look at the two object addresses for x and y now, they are different. They are no longer the same object. So something happened when we modified y that made it into its own object. And this is called copy on modify. So it only makes a new object when you modify them to be different. We can see when an object gets copied with this function called tracemem. So you can just set this up by, again, looking at this vector of 1, 2, 3, and then using this tracemem kind of function. And we're doing the same thing where we just assign 4 to the third value in the vector. For some reason, this is a known bug with R Markdown, apparently, with tracemem, is that it gives you this weird error message that I can't actually get rid of. But you can see here that the tracemem is saying that that a new object was created when we did this assignment. And it looks better if we just go to R itself and look at it. So we can see here, this is saying, there was, X was this or Y was this object, which was the same as X. And then when we assigned 4 to that third value, we copied and created a new object, and that has a new assignment. The other thing I will note, you'll notice there's this L here at the end of the integer. Does anyone know what that means? Because I didn't know what that meant. Oh yes, I'm using RStudio, not Visual Studio Code. Yeah, so I learned that that L means it's a long integer. Apparently that's, like, so integers in R can range from a certain minimum to a certain maximum. And if you want it to range larger than that, you have to specify that it is a long integer by putting an L at the end. I don't know why he's doing it for a value of 4. Maybe it's just one of those, like, programming best practices. I don't know. He doesn't really specify why he does that, but it was interesting to learn. And you can turn off that trace mem by using untrace mem, so you no longer get that message about everything that's being done. You can also trace mem for function calls. So we'll learn more about functions in a future chapter, but for now we know that we're doing this function that we are calling f, and it's just an identity function. It takes some value a and returns a value a. It's not doing anything to that value. You could do stuff within this function. You could calculate the mean, the standard deviation. You could do any number of things, in a function. But for now, we're just doing an identity function. And then we're taking our vector, and we're taking a look at what is going on within this function, like memory-wise. And because it's an identity function, nothing actually changes. It stays the same. There's no copy made because nothing was done to it. So even though we had a function, nothing about the object, our vector, changed. So there is no copy that is modified. And just some like diagrammatic ways of looking at this. We've got our function, which is denoted by this kind of, he called it a yellow box. I thought it looked like kind of like a price tag almost. We've got this yellow price tag over here, which represents our function. It had that argument a, which is bound when we run the function. So it's just saying that we bind a to x, but it's basically saying we're just looking at the same object. We're not changing it at all. So that vector is still that vector. And once the function completes, and we create some variable z, they point to the same object. So that name z and x are still referring to the same object, even after our function runs. So the important part here is that functions, if it ends up with the same object as well, that it's not going to create a copy of it. So another type of object that we use commonly in R is a list. Lists are similar to vectors, but they don't store values themselves. It stores references to them. And this will be an important distinction because it's not storing in the list itself, 1, 2, and 3. It's storing a reference to 1, a reference to 2, and a reference to 3. And we'll see why that's important in just a second. So we define one list, 1, 2, 3, and we assign it two names, L1 and L2. And then if we change one of those values in L2, the third value, and we change it to 4, we now see that our lists for positions 1 and 2 are still pointing at the same objects for 1 and 2. It's only the third value that is now pointing to a different reference. And this has very important implications for memory usage, which we'll get into. There'll be an example in just a second. So this modified copy that we've created is called a shallow copy because the list object and its bindings are copied, but the values pointed to, so those 1, 2, 3, are not changed. Only the object itself, and its bindings have been changed, but not the values. And we can convince ourselves of this by looking at what these two objects, what the addresses are. So we can see that we've got these two separate lists. The first two numbers, that's the 1 and the 2 positions, both are the same in both lists. It is only the third one that differs. So another common data object that we will work with is a data frame. Data frames are lists of vectors. And so as we can see here, we can represent our data frame as, two lists. Each of those lists has a set of numbers in it, which is a vector. So the vector is a reference, not a value. And if you modify a column in a data frame, only that column needs to be modified and the others will point to the original references. So in this case, we take our data frame D1, we bind the name D2 to it, and then in D2, we take the second column and we multiply that second column, every value in it, by 2. So what was 2, 4, 3 will be replaced with 4, 8, and 6. And we can see now that in our data frames D1 and D2, the first column still points towards that first, both point towards that first reference, that first vector. The second column in the first data frame is pointing to that original vector, but now for the second data frame, we've created this third vector that it is now pointing to. This is different if you modify a row. So this previous example was modifying a column, but if you modify a row, that changes things. Every column is modified, and therefore it is copied, and essentially at this point they become two separate objects. So again, we make a copy of D1, this time calling it D3. We take D3, we take the first row, and we multiply every value in that first row by 3. So 1 becomes 3, 2 becomes 6, but the second and third rows don't change. But because of how these data are stored, that you have to create new columns for each of them, so they essentially are separate objects at this point because you modified both columns. The important thing here is that this means that row-wise operations, that is operations that you apply to every row, are very computationally expensive in terms of memory use and efficiency in terms of when you're doing functions, because you have to define a new object. Essentially, you're copying over a new object instead of just keeping references to an older object. And finally, the other type of data that commonly is used in R is a character vector. So a numeric vector is numbers, a character vector is characters, strings. So we've got a character vector here of the letters A, B, C, and D assigned to the name X. This is the common kind of nomenclature, but this is actually not how it's truly being stored. Excuse me. In fact, R actually stores it using what's called a global string pool. So like every character is stored in some reference somewhere, some big reference that has A through Z in it. And then when you actually define the character vector, it just points to that global string pool to values in it. I think this is just, it does it this way to support, having lots of different types of characters, different languages and different alphabets and whatnot. And this allows them to kind of work like that. The book just mentions it as kind of like an interesting thing, but I don't think it's that important. So we'll start with why is our exercises with why is trace mem, in a vector of 1 through 10, why is that not useful? Well, why don't we try it and see what happens? Trace mem 1 through 10. Well, it gives me a value, but we didn't really, I think that the answer here is there isn't an object associated, like there's an object, but we haven't given it a name. We haven't looked at any operation applied to that object. So it's really just telling us that there is an object. Then explain why tracemem shows 2 copies when you run this code. Hint, carefully look at the difference between this code and the code shown earlier in this section. So we are defining a vector with 1, 2, and 3, X. We're then doing a trace memory We then assign a value of 4 to x, to the third value in x. So why do you think that is? So why don't we look at the difference? Let me switch to RStudio. We can look at the difference here. Let's see, where was that? So if we look at the trace mem we get here, we see that it is in fact it's copying it over. So why is that the case here, but not, and we'll get the other one and put it side by side so we can convince ourselves and see what's going on. And so what is different here? Any thoughts? And sorry, I can make this better so you can see it all.
We changed the third, right? The third place.
Well, it seems like we changed the third place on both of them, right? Part of me was wondering if this has to do something with the difference between the long integers and the integers. Oh, Marcel, Debble needs more memory. Marcel, would you like to say more about that? Because I don't know too much about that.
The 4, if you do type of 4,
Sure.
it's a double. And that needs more memory to allocate than the integers. So if you're replacing the third value of the integers, you're gonna have to create another copy to create a whole vector of double.
Oh, interesting. Okay. So would you like to explain to us? Because I think people might know what the difference between a double and an integer is. Putting
These
you
are
on the
just
spot.
these are types. Not sure exactly how much memory they use, but generally the integers use up less memory because double can be like decimal place, right? 4.5. So that would require more memory allocated.
Okay. Thank you. So yeah, so yeah, the double needs more memory. Okay. Thanks, Marcel. That was really helpful. Okay, and then it asks us to sketch out the relationship between the following objects. No, sorry, my cat. A, B, and C. Does anyone want to take a stab at how these are related, or want to sketch it out themselves? I can share a whiteboard if you want to sketch. Does anyone want to be brave?
Isn't it one is a vector? The first is a vector, the second is a data frame with 2 vectors, and the third is a data frame with 3 of the vectors, and they're all the same.
Are they data frames or what are they?
Oh, they're lists. I'm sorry.
Yeah. Yeah, so I think you're getting at what I thought this was going to be. So like, yeah, we've defined this vector A, which is 1 through 10. We then create a list that's 2 copies of A, so it should be just pointing at A for each column, is the object that is assigned the name A. And then for C, I think you can you can have a list of lists, so we'll have that list of A and A in B, which is still pointing at A because I don't think that object has changed. We'll also have A, and then we'll have this separate vector of 1 through 10 because we define that separately.
Similar to the first question.
Yeah. You can sketch that out for yourself and take a look at the object addresses if you want to see what's going on there, but we only have 20 minutes left and we need to keep moving. What happens when you run this code? Draw a picture. Let's find out what happens when we run this code. So we define some list of 1 through 10. We then take the second value in that list and assign it x. So let's see what x is now. So it looks like we have a list with two, so we can look at, so we've got the first object in that list is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Second object in that list is another list with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we've done is we've put this vector into a list, or this list into another list as a reference in that list. Again, I feel like this is one of those things where you just have to sit there and play around with it yourself and try and imagine what is going on, and then it'll make more sense. Moving on to object size, we can determine how much memory is being used using in the lobster package this object size function. So you can see, for the variable, I think this just contains all the letters in it. That takes up 1.7 kilobytes. If we look at something a little larger, so ggplot2 has some object called diamonds that takes up 3.5 megabytes. Lists are often smaller because they are references to values, and character values use the global string pool and are also smaller than expected. So if we take this object banana, which we name banana, I should say, which is bananas, 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 we see the object size of it is 136 bytes. But if we repeat that 100 times, so we have 300 bananas, the object is not 300 times 136 bytes. It's only, what is this, about 6 times larger, I would say 7 times larger. That is because it is storing stuff in the global string pool and is therefore smaller than we would expect. R also uses something called alternative representation. So for certain vectors, they can be stored more compactly than you might imagine. So if we imagine a vector of 1 through 3, that takes like 680 bytes. If we have one of 1 through 1 to the, or 1 to the, is that 10 to the third power? Something, 1 e to the third power, I guess, still takes up the same amount of storage space, even if we exponentiate, even as it gets exponentially bigger, it's still using the same amount of storage. So some exercises. In the following example, why are object size Y and object size Y so radically different? Consult the documentation of object size. I looked into this. Object.size, I think, is trying to estimate the actual total object size, including the references. Whereas object size wise is just the object itself, not including the references. Take the following list. Why is its size somewhat misleading? And I think this is, again, is because these are references, not the actual functions themselves of mean, standard deviation, and variance, which are larger. Because if you look at, like, we can take a look at one of these real quick. Object size mean. It's 1. Well, it does seem to add up to about 17.55. So I'm not sure why its size is somewhat misleading. Any thoughts on that? I
I tried to use AI to answer this, and it said
Yeah.
it has to do with where the object is pointing.
Okay.
I'm not sure if that helps. It says the size of the list only includes the size of the pointers to the object that are pointed to by the list.
Yeah, so it's the references, not the, okay. So let's try object size and see if that gives us something different for like this. Oh, see, so that is much bigger. So it's 35, because, oh, okay. So that's like 35 kilobytes, really. Okay. So yeah, there's references probably within the references to those functions, and it's probably not including those.
Yeah.
So predict the output of the following code. I did it. It's all the same size for these three, except when you start. So this first one is just not
Hi,
even sure.
Chloe.
Oh, hi.
So this is Andre. I
Yeah.
was thinking, I see a run if over there.
Yeah.
Uh,
See what that does.
is it like a random number generator or something?
Yeah, this seems to be generating a bunch of random numbers. We can see what the function does by taking a look. Oh, so there's a random uniform distribution. So it's just distributing a bunch of numbers around a uniform distribution. So and then so we've defined it, that is a vector that we've defined. And then if we create a list that's just pointing at that vector twice, it takes up the same memory. And even if we create a list that contains that list again and that vector, it's still pointing at that same object. So it's the same amount of memory according to object size. Now, if we look at that second list we defined and replace one of the values, we define we've modified it, so we've copied on modify, and that makes it double in size. And now that we've done that, it's doubled in size everywhere. And then we again modify it, but this time we've modified it so that, whoops, that both lists within B are the same again, and so the object size does not increase. But then when we look at it compared to A, which is now a different object that was unmodified, it has increased in size. Again, we've got like 13 minutes left. Play around with this on your own and it will make sense, I promise. Modify in place. So modify an object, as we've learned, usually creates a copy, but there are two exceptions. Objects with a single binding get a special performance optimization, and environments are always modified in place. We'll discuss what environments are in a future chapter, but for now we just know that they are modified in place. So what this means is when we modify an object with a single name, a single binding, it's always just going to stay the same object. So it's not creating a copy of that object, it's still the same object. There are some complications. So if you, for some reason, defined, like two different bindings, so two different names, and then removed one of those bindings, R still thinks that there is more than one binding and will still make copies even when it doesn't need to. And some functions from C will behave differently. What the long and short of that means is it's sometimes hard to tell if a copy will occur. Check trace mem to be sure. This is an example of where that can occur. This is a for loop. Again, it kind of looks awful due to a bug in the markdown, but if we look at it here, we can see the trace memory where oh, sorry, there was more in here, wasn't there? Yes, sorry. So for loops. So for loops are notorious for being slow in R. This is often due to each loop creating a copy. And so if we do this, if we take this data frame, which has 5 columns, and we can take a look at what that looks like real quick here. So it's just got 5 columns with a bunch of uniformly random values in it. Then we try and calculate the median for each using a function. We can, it takes a while to, it doesn't take a while to run, but it uses a lot of memory, and that's because it is, for each of those loops, it is creating a separate data frame. And that's not great. So the better way to handle that would be to use a list instead of a data frame. And if we do that here, we see even though it would give us the same results, it is not creating a bunch of extra data frames. Again, you could try this out on your own and see why. I wasn't sure why the list does it or doesn't do it, but the data frame does. So something to learn more about. Then finally, there's environments. They are always modified in place. This property is called reference semantics. I'm not really sure, what environments are used for, but essentially, we can define an environment that contains 3 values of A equals 1, B equals 2, and C equals 3. We define a second environment, and if we modify that environment 1, we see that environment 2, the value C is also modified. So even though they're separate names, if you modify one, it modifies the other. And this allows you to create functions that remember the previous states, which the usefulness of will be explored in further in future chapters. So explain why the following code doesn't create a circular list. Well, let's try it and see what we get, as always. We just get an empty list that just says that there is one value and there's a list in there that is empty, but there's nothing in that list. So why doesn't it create a circular list? Any thoughts?
Is it because the X is already empty?
Yeah, I think it has something to do with that, like that as we defined X as empty, and then we're just assigning this empty X, it's evaluated at the time of assignment, I guess, at the time of binding. And so it doesn't just keep binding it infinitely down into like an infinite list of lists. Yeah. Hi, Shaima. By the way, it's nice to hear from you. It's been a long time.
Yes, hi, Troy.
Sorry. Just excited to see you.
Thank
Wrap the 2 methods for subtracting medians into 2 functions and use the bench package to carefully compare their speeds. How does performance change as the number of columns increase? So you can try this out on your own. So this is the one that uses the data frame versus the one that works on the list. You can try this out for yourself using the bench package, and you'll see the performance change between the list version versus the data frame version is quite substantial when you have a lot of columns. So what happens when you attempt to use tracemem on an environment? Let's find out. So we've got E1 and E2, so it's tracemem on E1. Tracemem is not useful for promise and environment objects. So we can't figure out from tracemem how much memory an environment is using. Okay, so finally we've got unbinding in the garbage collector. You can unbind names from objects using the rm function. So if we define some vector x and use or define some vector and assign it the value x, or the name x, I should say. I'm trying to be very careful. We can then remove that binding by saying rm parentheses x. And then we end up with this unbound values. So we unbound the name, but what actually deletes the object? Because we didn't delete the object, we just unbound the name. That's something called the garbage collector, which is often called the GC. The garbage collector is tracing, which means it tracks every object in the global environment and all objects within those objects. So, you know, the vectors within a list or the lists within a data frame or however you store your objects, it knows about them. And the garbage collector runs automatically whenever R needs more memory to create a new object. You can also force the garbage collector to run using the GC function. But the book says you should hardly ever need to use this. Generally speaking, you should only need to do this if you know, like it didn't really give any examples where you would need to manually run the garbage collector. It said when it's needed, it will automatically run typically. And with that, we are done with chapter 2. I know that was a bit of a whirlwind. We had a lot to cover. We've got 5 minutes left for questions. Oh. Thanks, Jen. I think I can start talking and people have questions, feel free to interrupt me. I think the most important lesson from this chapter to me was the idea of how binding works, how the name is kind of separate from the object itself, and that how copy on modify works in terms of we R creates a copy of that object only when we modify that object, even if we have assigned it multiple names. I think that's the most important thing, and also kind of learning a little bit more about how lists and data frames differ. Those are kind of the big points I would take home from this. And then there's some useful functions for, you know, kind of looking under the hood and seeing what R is actually doing. Yeah, and with that, I will again plug that, hold on, let me pull it up. You can sign up to present at github.com, Walden Rab Data Science Seminar. The instructions on how to get started are listed under the README. And you can just sign up on the wiki. So next week, Jackie will present chapter 3. Thank you for being brave and volunteering, Jackie. I really appreciate that. And if you have any additional questions as you're working through this, feel free to post on the Google group. I think that one's wrong. Actually, I think I created a different Google group for us. Yeah, here. Feel free to post questions on the Google group. Yeah, and if there's nothing else, I think we can call it here. Thank you everyone for attending, and I'll talk to you next week.
Thanks, Chloe.
Thank you.
Bye.
Bye bye.